Okay, so let's begin. This was the first example of the quizzes that you will have frequently during the semester. Let's just go over the answers. Show that A and B are perpendicular. Remember the definition of the scalar product. Okay, this is the definition of the scalar product. So if two vectors are perpendicular, it just means the angle between them is 90 degrees. Cosine of 90 degrees is 0. So if you just take the scalar product of two vectors, if you find 0, then the two vectors are perpendicular. Right, basically, if you calculate this thing and find that it is 0, then you would have proven that the two vectors are perpendicular. Of course, in the second part, you could use that, because in the first part, I'm already telling you that it is perpendicular. Well, how to take the scalar product of two vectors whose components you know? So, of course, this is a definition if you know the angle between them. But since I just gave you arbitrary two vectors, beforehand, you don't know the angle between them. But then you can use this definition. If you have two vectors, the scalar product is just multiply the corresponding terms, components, and sum them up. The x component of A, the x component of B multiplied, plus the y components multiplied, plus the z components multiplied. And if you go to our vectors, the product of the x components is 1. The product of the y components is 1, 1 plus 1, 2. The product of the z components is minus 2, 2 minus 2 is 0. So I have these two vectors. The scalar product is 0, which means that they are perpendicular. The sum, well, just sum the corresponding components. A plus B is x hat plus x hat, 2x hat, plus y hat plus y hat, 2y hat, plus z hat minus 2z hat is minus z hat. So A plus B is 2x hat, 2y hat, minus z hat. A minus B, just subtract the components. X hat minus x hat is 0. Y hat minus y hat is 0. Z hat minus 2z hat is 3z hat. So A minus B is 3z hat. A dot B, we had just shown that it is 0. Well, the magnitude of A, let's again go back to the definition of the scalar product. If you just assume that these A and B vectors are the same vectors, then A dot B is nothing but A dot A is the magnitude of A squared. The angle between them is 0. So cosine of 0 is 1. So the magnitude of a vector squared is nothing but the vector scalar product with itself. Yep. So the, oops, sorry. So the magnitude of A squared is just A dot A. It is 1 squared plus 1 squared plus 1 squared, which is 3. So magnitude of A is square root of 3. For B, it is 1 here, 1 squared plus 1 squared plus minus 2 squared, which is 4. 4 plus 1, 6. So the magnitude of B is square root of 6. So if I give you the same quiz again now, what would you do? You think you will do all of them? No. Why not? So what's not clear?
I didn't understand the second question.
This one.
Last part.
A dot B.
Yes.
A dot B, how, well, this is also the first part. A dot B. Yes. It's just multiply the corresponding components, sum them up. It is this one that we are using. I'm multiplying the x components, adding the product of y components, adding the product of z components. For any vector, I can always calculate the scalar product either like this, if I know the components, or like this, if I know the lengths and the angle between them. Both are equal.
When we show, for example, ax is a number, ay is another number, az is another number, what do I have to imagine in my mind? I cannot understand it.
Well, what this tells me is, let's say, okay, let's just take to this example. Ax is 1, ay is 1, az is 1. What you should imagine is, if this is my origin, my x-axis in that direction, y-axis in that direction, z-axis in that direction, this tells me that, and the unit I use, let's say, is a step. It says 1 step along x, 1 step along y, and then 1 step along z. Well, I need to climb over here. So that is this vector over here. Okay, so that 1, 1, 1 vector is in fact, with these coordinate axes, it is a vector starting from here, going up to here. This is the vector. This is my vector.
Can you show that they are perpendicular while you make?
Either by drawing, well, if you are a good drawer, if you can draw quite precisely, or you can say that, okay, if you want to prove that they are perpendicular, calculate the scalar product. If it is 0, then they are perpendicular. Yes?
Some reference books show the axis with I, E, K.
Like your book, like the book of this lecture, yes?
Are these the same?
They are exactly the same. I hat is x hat. They are just how you want to denote the vector along the x direction. Well, I prefer this x hat, y hat, z hat because their name already contains the direction. So x hat, the unit vectors are mostly denoted by this hat notation. X hat is a unit vector along the x direction. This I, j, k, it's the same thing. I hat is nothing but x hat, but I prefer this one. If it's confusing, I can switch to this IJK. Any other questions? Okay, so the lesson from the comments that I have had after the quizzes, by the way, before going on, even if you couldn't do anything in the quiz, you should hand in your quiz. Because remember, the quizzes will also, it's not just the grade that you obtain in the quizzes, but your participation in the quizzes will affect whether you can take the final or not. So even if it's just an empty sheet, just hand it in. So I would like to repeat the things I had in the first lecture. You should study regularly, not just before the exams, because some of the exams you will not know when they will be. Come to the class having read the things that we will be discussing in the book. We are following the outline of the book mainly, so it's not, I don't even need to tell you what we will be doing in the next section, next hour, because it is what is in the book after these vectors. So they are important. Work regularly, come to the lecture having read the material. Yes? From the book? Well, you should read it, at least. In the homeworks, you can get some of the problems. I can give you some problems from the book to solve during the homework. I didn't use the book yet, but I will probably use it later on. I don't remember. I don't think your book has any questions on the Lord of the Rings, so I don't know if I will be using it. Well, the credit of the homework goes to your assistant, by the way. He was the one to prepare the homework. Any other questions? Yes? The course ID is, well, instead of, it's 109, 23000109. That is our course ID. This is the course ID. We will not be using the website of the book, by the way.
The book gave just the odd numbers, answers, for answers, they gave only odd numbers.
Okay.
Where can we now?
Well, that is a question that you shouldn't ask to your instructors. I mean, the thing about the having solution manual at hand is, I mean, all these 4 years, just imagine it as a play that will prepare you to the real life. I mean, all the questions that we are going to ask you will have some solutions. But when you become a physicist, the nature will not come with a solutions manual. So you should also develop this sense of judging whether you have done is correct or not. If it is not correct, then looking at the solutions manual and finding the solution doesn't really mean anything, because if you cannot solve the questions, it means that there is some subjects that you haven't yet understood. Even if you get it from the solutions manual, you still wouldn't be understanding the subject, and that is what should count. And if you have the solutions manual, I'm sure you will, I mean, just asking around. At most, the third student will tell you where to get the solutions manual, at most. But if you get the solutions manual, even if you say, okay, I will not look at the solutions manual until I find my answer, it will last a few days at most. After that, at first struggle, you will just open the solutions manual, and it will be bad for you. If in your judgment, what you have done is wrong, then repeat the subject. There's something you didn't understand there. If you judge that it is correct, compare it with a friend and see who will be able to convince whom. It's most probably, I mean, if you have different answers, it's most probably the one of you who has got the right answer will convince the other one. Your friend was asking me whether his answer was correct or not. When you go to the real life, whether a given answer is correct or not, you usually discover it after tens of years. You make your arguments, somebody else makes counter-arguments, a third person makes a completely different argument, and only when the experiments can really measure it, then you can have then, in quotes, you can tell whether one is correct or the other one. But you have to live for 10 years not really knowing whether the answer is correct or not. Any questions? Questions about the vectors, because we will be using vectors now. Projection, yes. So this is the definition of the scalar product. A dot B is the length of A, the length of B times the cosine of the angle between them. This is how we define it. But the thing is, how can we interpret this thing? If you look at the geometrical picture, I have this A vector, I have this B vector. From the tip of the A vector, okay, when I draw these things, don't get it confused. This vector is at this point. This length just shows the size of the vector. And the length of this line shows the size of the other vector. But the vector is a property of this point only. So if I look at this diagram, from the tip of my vector A, I can just draw a perpendicular towards the B. This is a right triangle. If you remember the definition of the cosine of alpha is just the length of this side divided by the length of this side. Or I can say the length of this side is nothing but the vector A times cosine of alpha. The vector A times cosine of alpha, A cosine of alpha, here I have A cosine alpha, it just gives me this length over here, which I denoted by A parallel. The length of the component of A parallel to the vector B. Or this is A times cosine alpha is A parallel. Or I can repeat the same thing, just take from the tip of the vector B, I can draw a perpendicular to the vector A. This is a perpendicular line. Here I have another right triangle. The length of this side is the length of B times, again, cosine of alpha. So the length of B times cosine alpha is this length over here, which I denote by B parallel. Well, I can repeat the same thing for the cross product. Since it's a sine, it will not be the parallel component, but it is this perpendicular component. A cross B, the magnitude of A cross B, I can write as B, the length of B times the length of the perpendicular component of A to B, or the component of A, the length of the component of A perpendicular to B. Other questions? Oh, by the way, there were some comments that saying that, oh, you didn't understand some subjects. Okay, at the beginning of each course, I will be asking you if you have any questions. That is the point where you should ask me. If there is something, assuming that you have already read the book, the relevant chapters, went over my slides or your lecture notes, and you still didn't understand it, then at the beginning of the course, just ask me. Ask the class. Most probably, or at least half of you would be looking for the answer of the same question. The quizzes will always come after that one. I will never have quizzes before asking you if you have any questions. Okay, there is an announcement by your assistants. One thing is piazza.com, which I mentioned at the first lecture. It is a site where you can ask questions anonymously. Nobody will know that it is you who is asking the question. So even if you think that your question is really stupid, you can ask it there and nobody will guess it was you. Use Piazza. So your assistant says that, okay, on Tuesday you have already decided the hours, recitation hours that you will be doing. There will be 2 physical recitations, 1 online recitation, but you should choose which recitation you will be going to. So because the assistants will also read, I mean, if you go to one recitation, that assistant will be reading your homeworks. Just write to your assistant. I will send you this email. Email your assistant which recitation hour you would like to join. Let him know. And the details, once you register to piazza.com, there are details also there of this course. Currently, there is nobody registered at piazza.com. Questions? Now let's continue with motion in 3D. We had already studied motion in 1 dimension. If you remember, in the motion in 1 dimension, the first thing we did was to discuss how we can specify the position of an object. We had taken a line, the motion was along this line, and telling the distance between a chosen point origin. If you just tell me at which side it is, on the positive side or the negative side, and if you tell me the distance of the object from my origin, then I would know definitely, without any ambiguity, the position of my object. Well, in 3 dimensions, things get a bit more complicated, because just a number is not enough. I have to tell the direction also, and that is where the vectors come into the game. So I need to specify where is the position of your friend without any ambiguity, and I should be able to tell my colleagues that he is at such and such a location. So for that, I use vectors. So this can be the trajectory, an arbitrary trajectory of my object, this black thin line. It's moving in this direction. At some point, your friend can be here. I can specify that point. Well, this is my origin. This is my reference point. You can choose it any way you like. Just choose any reference point that suits you. And then you can imagine the vector pointing from the origin towards the position of your object. Remember, the vector has two information, the length and the direction. So this vector tells me that your friend is in that direction. It gives me the direction. It also contains a length. It also tells me how far away your friend is in that direction. So this is the vector x1. Of course, your friend will be moving around. He will not be sitting there. So he will move up, down, and up again. And at some later time, I will see that he is here. At first he was there, but now he is over there. So this is the second position. Well, I can talk about his displacement. Well, when I mean by his displacement, well, he can tell me that initially he was here, and finally he was this many meters in that direction. Now, that is a vector. So this is the displacement vector we have, which we denote by, okay, this delta. Delta x, that is the change in the x vector, which I use to denote the position, the change in the position, which I can also say as the x vector from 1 to, these are just notations, by the way. Especially when you are dealing with complicated problems, which will contain lots of different symbols, your symbol should contain some, should be self-explanatory. X is quite conventional for position, just like R. Delta x, change in x. x12 is the x vector, the position vector, or the displacement vector from point 1 to point 2. This is my point 1, this is my point 2. And I can just write it as the change in x, the change in something, in anything, is nothing but its final value minus its initial value. So my object is moving along this line. So I just measure the position of my object at two different times. At the final time, it's at position x2. At the initial first measurement, it's at x1. So the change in its position is x2 minus x1. So that gives me the position, the change in the position. Well, just like in one-dimensional motion, we are interested in the rate of change in the motion. That is the change in the motion per second. Well, I have the x initial, x final. Delta x is the final position minus the initial position. The average velocity, if you remember in the one-dimensional analog, we define the average velocity as the change in position in a given time. So delta x is the change in position, delta t is the given time. So how long it takes for my object to move from the initial point to the final point. It's again exactly the same thing. Delta x, I need to take the difference of two vectors, which, well, we had covered, but from your comments to the quizzes, which you haven't yet learned, but learn it today. You can take the differences of two vectors. That will give me delta x. I can just multiply or divide the vector by a number. This is also an operation that we had discussed. Component-wise, it is nothing but just divide all components of this vector by this number. So I can, all these operations, we know how to do it. If you have to sit on a table and calculate it with paper and pen, you know how to calculate the differences, you know how to calculate, how to divide a vector by a number. These things you can calculate. Well, you can of course talk, here I have two vectors equal to each other, but we had already said that if you have two vectors equal to each other, they should have the same components. Well, the x component of the average vector is equal to the x component of the change in the position of my object divided by delta t. The y component is the change in the y position divided by delta t. The z component is the change in the z position divided by delta t. Well, up to this point, everything is as if all these three directions are completely independent. The x average velocity in the x direction doesn't depend on the displacement in the y direction at all. So they are completely independent. It's as if the three-directional motion is nothing but three independent one-dimensional motion. And so we will be using this to generalize the concepts of the instantaneous velocity. Well, the instantaneous velocity is just take the limit as this delta t goes to 0. So rather than taking large time intervals at t equal to 0, I am here. At t equal to 2 seconds, I am here. So you calculate the average velocity. To obtain the instantaneous velocity at t equal to 0, you should measure my position at t equal to 0. And then at t equal to 0.00001 seconds, measure my displacement, divide by the time, and that will give me my instantaneous velocity at t equal to 0. Or it's just the derivative of my position with respect to time. Again, you can just write it in terms of components. The derivative, well, the x hat, y hat, and z hat component vectors, they do not change in time. They're just constants. X hat vector is pointing, if this is my positive x-axis, my x hat vector is in that direction. It doesn't change in time. So in taking these derivatives, I can just ignore its time change. So the x component is nothing but the derivative of the x component of the position of my object with respect to time. The same thing with y and z. Again, here the discussion is almost identical to 3 independent one-dimensional motion. Acceleration is the same story. Again, we are just copying everything from one-dimensional motion to three-dimensional motion. By the way, this is why I will keep telling that it is important that you study regularly. If you understand one-dimensional motion, three-dimensional motion is just a copy of the one-dimensional motion. Just take 3 independent one-dimensional motion and you get the three-dimensional motion. Well, in the one-dimensional case, we said that the change in the velocity is what we define the acceleration. The same thing here. The change in the velocity per unit time is my average acceleration. If I have a large, if I measure my velocity at t equal to 0 and t equal to 2, take the difference in the change in the velocity, divide by 2 seconds, that would give me the average acceleration of my object between t equal to 0, t equal to 2 seconds. Again, it's just component-wise. You can also write the acceleration vector is nothing but the acceleration along the x direction plus acceleration along the y direction plus acceleration along the z direction. They are completely independent motion. And instantaneous acceleration, I'll take the limit as delta t goes to 0. And it just becomes the derivative. This is the definition of a derivative of a vector, by the way. Well, rather than writing x, y, z components all the time, quite often I will be using this notation. AI of t is dvi over dt, where I can be x, y, or z. So this is, in fact, stands for 3 different equations, not just 1, but 3, for each possible value of I. And now we are back to integrals. Remember, integral is a sum. I'm just summing over different contributions. So we know that the velocity we had defined as the rate of change of the position. If I want to invert this one, the position of an object at time t is nothing but the position of my object at time ti. Let's just suppose that I would like to find the position of my object at t equal to 5 seconds. Initially, I'm here at this point. At t equal to 5 seconds, where will I be? Well, I have some velocity at this moment. If I look at t equal to 1 second, my position will be this position. Suppose my velocity is in that direction and it doesn't change in the first second. So at t equal to 0, I am here. At t equal to 1, I will be my velocity times 1 second. I will be here. I added that difference to my position. At this point, suppose that my velocity is there. 1 second later, I will be here. Another second later, if my velocity is in that direction, another second, I will be here. I just sum up all these changes in up to 5 seconds, and then I will be reaching here. This will be my position at 5 seconds. This is this equation and nothing else. So v times the dt, I'm just dividing my time interval into very small parts. 5 seconds, I'm not dividing into 5, but let's say 500 equally spaced time intervals, each with having a length dt. at each one of these time intervals, my displacement will be the velocity at that time times the length of that time interval. This is the displacement within that time interval. And if I sum all my displacement between the initial time to the final time, I get my total displacement. If xi is my initial, this is my initial position, this is my displacement, I sum them to, this gives me my final position. Well, for the velocity, it's the same thing. If I'm interested in my velocity at some later time t, I have to calculate all the very small changes in my velocity due to this acceleration and add it to my initial velocity. That will give me my final velocity. So each one of these, a times dt, is a very small change in the velocity within a time interval of length dt prime. I'm just summing them all up, this is this integral, to obtain my final velocity. Now let's do an example. Motion in Earth's gravity. So how does the object move? If I just throw an object. Okay, so no. If you just throw an object, it will just go up and down. And if I throw these two objects at the same time from the same point, they will all fall almost at the same time on the ground. They have quite different weights, but they will still fall with the same acceleration. Of course, this is not true if I just take a piece of paper and draw these two things. They will, of course, fall at different rates. This will fall first, this will fall, I don't know when, because of the air resistance.
What I cannot understand, even without friction, the heavy object will have more force.
True.
It should fall
First. Now, we will see it when we study dynamics. Your friend is right. If I consider these two objects, this is quite light, this is relatively heavy. If I could evacuate the air here and drop these two things at the same time, they will fall on the ground at the same time. But as your friend has said, the heavier object has a larger weight, so there is more force acting on it than the lighter object. So why doesn't it fall first? As we will see probably next week from Newton's dynamic, this has a larger weight, but it also has a larger resistance to change in its velocity. It has an inertia due to its larger mass. We will see mass and inertia, the relation between force and acceleration next week. This is observation. This is an observational fact that when you evacuate an area and drop two objects at the same time, they all fall at the same time, independent of their weight. This is, by the way, one of the observations led to the discovery of general relativity. This is closely related with general relativity. If this were not true, then we wouldn't have the theory of general relativity.
resistance to changing velocity is inertia.
Yes.
Normal situation air exists. The important thing is heavier or the
Both of them will affect. The size will affect the resistance of air. But if I drop this thing and my laptop at the same time, my laptop is heavier than this one, which I will not drop it, but if I do it, probably my laptop will fall first. Although it has a larger cross section, since it's heavier, it will fall first.
It's important to study in the Earth because you cannot throw a helium balloon.
Why do we need to throw an helium ball? Well, all of those things will have an effect. Okay, so now we have a nice blue screen. They claim that blue is like soothing to the soul. Your friend was not happy with the blue screen. So now, so close to the, this is also valid close to the surface. This is again, every object accelerates with the same acceleration, and that acceleration is 9.5 meters per second. And the direction of that acceleration is towards the center of the Earth, almost. Let's say approximately it is towards the center of the Earth. If the Earth had been a perfect sphere without any rotations, then it would have pointed towards the center of the Earth. But both rotation and the mountains around us, they modify the direction slightly. But approximately, we can just say that it is 9.8 meters per second squared towards the center of the Earth, which we call downwards. Well, as in any study of any kind of motion, the first thing you should do is just choose an axis, how you will describe the motion. Well, I will choose, this is again completely arbitrary, up to you, whichever way you like. This will be the direction of this is my positive z-axis. I choose it that way. My x and y axis, I will assume that they are along this direction. Well, I cannot show three-dimensional objects here, so this plane is the xy plane, and this is my z-axis. Well, then the acceleration is nothing but g, which is 9.8 meters per second squared, along the positive z direction. If I had chosen the z-axis upwards, I should have included a minus here, because g is by definition 9.8, positive number. Well, the velocity, we had just seen that velocity at a given time t is the velocity at a given initial time ti plus the changes in the velocity. Well, the acceleration is just constant. So if you have a constant thing, the average of it is equal to itself. So I just multiply the acceleration by the time change to obtain the change, well, the time to obtain the change in the velocity. So I started with this one. This is the change in my velocity. So my velocity at time t is given by this expression over here. And remember, this is in fact three different equations. It's not just a single equation. It is a vector equation. This vector is equal to this vector, which essentially means all three components of these two vectors are equal. Well, now I have the velocity, that is the rate of change of the position of my object. I can calculate its position at a given time. Well, the position at a given time is the initial position times the incremental changes in the position, each small step by small step. So if I just take the integral of that thing, well, vi is a constant, I can just take it out of the integral. The remaining is just t, the total time. Well, if you ignore this thing, this is motion with constant velocity. So the change in the position will be just the velocity times the time the motion lasted. So v times the duration of the motion gives me the displacement of the object. Then I have the acceleration piece, and it just brings me this part. The integral of t minus ti is just t minus ti squared over 2. So this much integration I do expect you to know. Just taking the integrals of polynomials. Integral of t, t squared, t cubed, you should be familiar with that much, at least. Well, this is the general theory. So now I have all the equations. I have derived the position of my object as a function of time, and the velocity of my object as a position of time. Now the rest is applying these expressions to particular cases and just deriving we will be studying this trajectory. When a football player hits a ball, so how does the ball move? In this simplified model, remember, we are assuming that the objects are point-like, they are not rotating, plus we are ignoring air friction. This will be an approximation. Before you leave Before you leave, sit down, sit down, sit down, sit down, sit down. Everybody, we still have 3 minutes. Questions? That we will come next week. Yes? A bit louder, please. Yes. Which one? This one. This VI is the initial velocity. It's a number. Well, the final velocity at the time t is given by this. This is the expression. If you use this formula, this expression for the velocity, and calculate the position, you get all this expression. Again, this VI is a constant number. It's not the velocity at the time t. It is its velocity at t equal to ti, the initial time. Other questions? Well, the lab hours, I'm receiving lots of questions about the hours of the labs. Well, the lab hours you will decide on the 9th. In 6 days, well, that is on next Wednesday at 2:40, you will meet in the lab. None of you should have any courses at that time. You should meet in the lab on the 2nd floor, and then you will divide into various groups, and you will just go to the group that fits your schedule. That will be determined next Wednesday. After next Wednesday, once you choose your groups, you will have an experiment every week.